e-learning program which has been started by SCMPCR, and in this series, this is the sixth program, and it is accredited by IOMP Accreditation Board. And in this direction, today's lecture will be on radiobiology of radiotherapy. So just because the co-organizers of this e-webinars or e-learning program is Global Access to Cancer, the foundation, Cancer Care Foundation is also there, and along with that, United International University is there. So we must understand the incidence of cancer across the world. And if you look at this thing in Asia, and if you include Oceania, half of the cancer come from this region, Asia Pacific or Asia Oceania region. 50% of the cancer are from this region, and socio-economically, this region is, you can have LMI countries, middle-income countries. So radiotherapy started just after the discovery of X-rays. X-rays were discovered on 8th November 1895. On 27th March 1896, Emile Grube used X-rays to treat breast cancer. And the discovery of radium-226 in 1898, again, the brachytherapy and the teletherapy has started with the radioisotope. So since last 125 years, radiotherapy has progressed rapidly as a main modality of the cancer treatment. Almost, you can say, 60% of the cancer patients are treated by radiotherapy singularly or in combination with surgery and or chemotherapy. So radiotherapy is the main modality of the cancer treatment. And if you look at most of the cancer, the first choice of treatment is the radiotherapy, either singularly or in combination. It is for the radical treatment as well as for the palliation treatment also it is used. So roughly 56% of the cancer patients worldwide live in this developing world, and these countries possess only 5 to 10% of the global resources available to battle this endemic and find immediate sustainable solution. Just I'm giving some idea. And if you look at this thing, in high-income countries, for 120,000 patients, there is a single radiotherapy machine. But if you look at the low-income countries like in our region, 5 million patients are served by the single radiotherapy machine. And that is what we are depriving the patients of the right for the treatment because the facilities are not available. Just some idea about the AFOM region also, if you take it, the countries, if you look at teletherapy machine per million population, Australia has got 14, but if you look at the Bangladesh, it's a 0.21 teletherapy units per million population. Also, if you look at India, it's a 0.47. So we have to go a long way for addition of these facilities. Similarly, medical physicists play a very important role into radiotherapy. And this year's IDMP theme is medical physics for sustainable healthcare. If healthcare has to sustain, the medical physicist or medical physics is very important. And this is what I have shown in teletherapy machines required, and the shortfall, if you see, in many countries, the availability just, you can say 10% or 20%. So 4-fold, 5-fold increment in the radiotherapy facilities is needed. And if you look at the number of medical physicists per million population, also in this region, there is huge heterogenicity 0.56 in Myanmar to 20 medical physicists in Australia. So almost you can say about 40 times a difference is there, and average is 2.67 medical physicists, which are important for radiotherapy. If you just compare with the USA, 24.5 medical physicists per million population, we have in AFOM region only 2.67. Just background I have given. Now I will come to the main topic of the webinar or this series, radiobiology and radiobiology of radiotherapy and cancer biology. I will speak in this during maybe 50-60 minutes. So radiobiology is a branch of science which combines the basic principle of physics and biology and is concerned with the action of ionizing radiation on biological tissues and living organisms. When the ionizing radiation interacts with the living organism, living tissue, how it interacts, what is its response, study of that is called as radiobiology. And when I'm talking about radiobiology, radiation is ionizing radiation. It's a way back in 1906, Bargoni and Tribundu irradiated scrotum of a ship by X-ray, because that time we had X-rays only, and they found, Bargoni and Tribundu, and that is the basis of our radiobiology, and they realized from the experiment of irradiating the scrotum of the ship that the cells are dividing, multiplying, are highly radiosensitive, because the sperms and the skin cells, the sensitivity, the response rate to the amount of radiation same was different, and they found that rapidly dividing, undifferentiated, have a long mitotic future, are highly radiosensitive. And as you know, human body is heterogeneous in terms of the cell cycle, cell proliferation, types of the cells, differentiated, undifferentiated, completely differentiated, and response to ionizing radiation, if you take it, lymphocytes and spermatogonia are highly radiosensitive. Osteoblasts, spermatids, muscle cells are medium radiosensitive. Nerve cells, which are completely differentiated, are radioresistant. However, once they are damaged, nerve cell damage to the spinal cord, damage to the brain, recovery is not there also. Tolerance is good, but still then you have to see that recovery is not there. Now, the sensitivity of a cell is not the same all the time, because cell is going into cycle of multiplication, and the sensitivity of the cell varies during different phases of its division. So radiation effect depends on the sensitivity of the cell. Sensitivity of the cell depends on the cell cycle. That's a cell in which phase. G1 phase, in which cell grow and becomes mature. S phase, synthetic phase, in which DNA synthesis, very active phase. G2 phase, in which cell division occurs, and M phase, which is a mitotic division, occurs there. And when division occurs, if you see, this is the cell cycle, and this for human from 6 hours minimum period to complete the cycle, to it can be 24 hours or 48 hours. And this is what different phases are given. This is the mitotic phase, and then cell that stages in division, then gap, then replication, then G2 prepare, divide. And if you look at the sensitivity, G1 phase is the most resistant, radio-resistant. S phase less resistant. G2 phase sensitive, but the most sensitive among the cell cycle is mitotic phase, which is most sensitive. And therefore, our radiotherapy fractionation schedule should be that we follow this mitotic phase for getting better control probability. Again, if you look at their relative survivability or sensitivity, G1 is most the resistant, and therefore relative survival will be maximum. S phase 0, and M is the most sensitive. So with the same radiation, the relative survival will be minimum into the M phase. Cell killing will be much higher in M phase. So we have to take into account this. Now, radiation when interacts with the human cell tissue, there are early effects and there are late effects. Early effects are hematological syndrome, the GI tract, NVD, nausea, vomiting, CNS syndrome, tissue damage, erythema, discoimation. These are the early effects, and they recover after the radiation assault is over. They may be 1 week, 2 weeks after that. Hematological damage, cytogenic damage, and late effects are the induction of leukemia, bone cancer, breast cancer, thyroid, local tissue damage, fibrosis, proctitis, cytogenic damage. These are the late effect which occurs, and therefore when you talk about the radiotherapy, we see what are the early effects which are manageable and what late complication after radiotherapy it is going to take place. Depending upon that thing, we decide number of fractions, the period during the fraction, and the total dose what we give, so that the complication, early effects are manageable and late complications are as minimum as possible. Now, when radiation interacts with the human cell, so there are two kinds of effect. One is an indirect route and another is a direct route. Indirect route, when ionizing radiation interacts with the water into the tissue, the cytoplasm, and then it produces the free radical OH or H, and these free radicals are highly chemically active and they take part into the damage and they create a damage. I will call about after what kind of damages will be there. I will discuss this thing. So this is called as an indirect route, wherein the ionizing radiation first ionizes the water, produces the free radical, and these free radical take into chemical reaction and then biological effect is produced. And where radiation directly hits the chromosome, directly hits and damages these things, then that is called as a direct hit. In case of X-ray and gamma rays, that is a non-particulate, do not have mass and charge, the effect is almost 90 to 95% is indirect route. But alpha particle, proton, particle radiation, neutron, that is called the direct effect, which I will discuss later on. So direct and indirect effect, again in little bit detail I am showing it here. Here when ionization takes place, electron is released and this will take part into this thing, and this happens with low LET. I will discuss what LET and all those things is. LET because X-rays and gamma rays has a very low LET, linear energy transfer of 0.25 Ku per micrometer. It happens indirect effect. And direct effect where alpha particles, the protons or carbon particles, there they produce, they are already charged and they hit directly, they have a very high LET radiation, that is called as a direct effect. Now again, direct action of the X-ray, very minimal. Indirect action by producing the water molecules and the free radical, reactive free radical, it is much higher, important component of our photon, that is X-ray, or from our gamma, it is 90 to 95% is indirect action. So direct action, biological damage occurs as a result of ionization of the atoms or a master or a key molecules, and that is mostly the water. Indirect action effects produced by reactive free radicals created by the interaction of radiation with the water molecule. This is an indirect effect, and direct is directly hitting, which is alpha particle, neutron, proton, or carbon. So high LET radiation damage to biological tissue by direct action, that is the alpha particles or the protons, and indirect effect, it's the interaction with water and formation of OH and H free radicals. And these free radical formation will get enhanced if there is a presence of more oxygen. So oxygen works as a catalyst for production of this OH and H, the free radicals, and the chemical reaction will increase, biological effect will increase. So in presence of oxygen, this free radical formation is much higher and the biological effect will be much higher triggered. This is called as the OER effect. It happens only with the indirect action, mostly with the X and gamma radiation. Again here, how the electron and then the free radicals are formed, it is shown. I will not go into the details of this thing. And out of OH and H free radical, OH is the most damage comes from this thing, and oxic cells or presence of oxygen will increase the production of this free radical, and the effect will enhance what is called as OER. Now, this process of indirect action takes place within fraction of second. See, incidence of the X-rays or photons within 10 raised to minus 15 seconds, fast electrons are created. These electrons then produce free radicals, and free radicals will take into chemical changes by breaking the bond, and they will result into biological process. Now, these chemical changes of free radicals which have been formed, now you can accelerate or decelerate the effect of this free radical, and end biological effect can be controlled by using radiosensitizers or radioprotectors. So radioprotector will scavenge, mostly sulfur drug, the free radicals and reduce the biological process or biological effect, and sensitizer will enhance. So many times we use the concurrent chemotherapy. So radiation with chemotherapy is sensitizing, or oxygen supply, that is again is sensitizer. And this biological effect process can continue for a day, for a week, or for a month also. So X-ray photon, fast electron, ion radical, free radical, then chemical changes, and finally results into the biological effect. And that I told you, this here you can control by radioprotectors or radiosensitizers, the end biological effect. Now, when radiation interacts with the cell, there are three possibilities. One is that the amount of radiation produces a damage such that cell cannot survive, cell death occurs. This is called as a lethal damage, means cell do not survive, cell gets killed, it's a lethal dose. Second possibility is that a minor damage taken place, but in a course the cell gets repaired and functions again as a normal cell. And third possibility is that there is a damage in a DNA and cell survives but as a mutated, as a atypical cell. So three possibilities are there: is lethal, that is a cell death occur, a repair take place, function as a normal cell again after the radiation, and the third possibility is that the DNA damage, mutation take place, cell functions as a atypical cell. Now we'll see the components which are determinant in the radiation biology, radiation effect. First is LET, linear energy transfer. When the ionizing radiation, let it be a photon or X-ray or alpha particle or electron, when enters into a tissue, into matter, it goes on depositing energy, KeV, per micrometer it traverses. That is called as linear energy transfer. For X and gamma rays, it is 0.25 keV per micrometer. For alpha particles, almost 2 MeV per micrometer. So LET is a linear energy transfer. RBE, I will define all the terms as we go ahead. RBE is relative biological effectiveness. We have different kind of radiation. It is alpha particle, it is charged particle, uncharged but have mass particle, or just photon, no mass, no charge, and also the tissue sensitivity, the environment is different. So relative biological effectiveness of the kind of radiation, that is called RBE, compared with 250 kV X-ray. OER is oxygen enhancement ratio in presence of oxygen, in absence of oxygen, what happens, that we'll see. So again, just in detail, the average energy deposited per unit length of the track, keV per micrometer, is called as LET, linear energy transfer. For alpha particle, you know, they are charged, they have mass. So in a very short distance, they deposit huge amount of energy, MeV per micrometer. So they are very high LET radiation. And X-rays, because they do not have mass, do not have charge, they penetrate long way, deposit the energy slowly. So they are low LET radiation, keV per micrometer. So gamma rays and X-rays are low LET radiation, and high LET radiations are alpha particle, ions of heavy nuclei, charged particle, low energy neutrons, because neutron has got LET different. High energy has got a low LET, low energy neutrons have got the high LET. And that when we talk about the radiation protection, we see quality factor for the neutron ranges from almost 2 to 7 or 8. Now RBE, relative biological effectiveness. So relative capacities of a radiation with the different LETs to produce particular biological response is called as RBE. So different LETs with how they produce, what effect they produce, that is a relative. And what is the RBE? Dose in gray from 250 kVp by X-ray divided by dose in gray of the test radiation to produce the same kind of effect, same kind of biological damage. For example, X-ray requires, say, 10 gray dose to produce a effect, and alpha particle requires only, say, 2 gray. Then 10 divided by 2 is equal to 5. So RBE is 5 for alpha particle. Just example, I taught how to calculate this RBE. Now again, here you can see determination of the RBE. If you look at this thing, the with radiation with X-ray we are giving, and particle therapy we are giving. So for 10% survival, amount of dose required by the particle therapy is this much. But for X-rays, dose required is much, much higher. So dose required by the X-rays is higher. Dose required by the particle therapy is less. So the RBE is always more than 1. So for the particulate radiation. For X-rays, it is taken as 1. So what is the relation between LET and RBE? As LET increases, RBE increases. So more the linear energy transfer, more the heavier particle, more the deposition of the energy per micrometer, radiobiological effectiveness will be much, much more. So that is what we do. And you know, during radiation protection also, we use the quality factor, and that depends upon actually LET, and that is what we call RBE. Now we'll see what is this OER, oxygen enhancement ratio, which is very, very important in the prognosis of the radiotherapy treatment. The ratio of the radiation dose required to cause a particular biological response of the cells or organism in an oxygen-deprived, anoxic environment to the radiation dose required to cause an identical response under normal oxygenation conditions. As I told you that this is oxygen enhancement ratio plays a big role in indirect kind of radiation action, because formation of the free radicals will be much more in presence of the oxygen, and therefore OER for X and gamma rays is much higher. It's almost 3. But if you look at the particulate radiation, it comes down and almost becomes 1. So for particle therapy, the cell or tumor is oxygenated or not oxygenated, the response remains the same. And therefore, where the solid tumors or the blood supply is much less, like a chordosarcomas, or we could not achieve the complete tumor regression by X or gamma radiation or the photons, then we can try the particulate radiation, which is independent of the oxygen presence, oxygen supply, or the blood circulation. So as LET increases, oxygen enhancement ratio comes down. So low LET, high OER. So X and gamma radiation is low LET, and therefore OER is a maximum. But alpha particles or carbon particle, LET is much higher, OER is approaches almost 1. Now, in radiotherapy, in last 125 years, huge amount of developments have taken place. And these developments are in terms of the technological advancements, in terms of the machine, accuracy of the dosimetry, the dose delivery, and second is the biological advances, understanding biology of the cancer, biology of radiation effect, and implementing or using it to optimum. Earlier, it was an isodose charts or isodose distribution to equal doses. Now, it is an ISO-ERD. I will explain that what is the extrapolated response dose, ISO-ETD or ISO-ERD. So now we are planning how much is a biologically effective dose, and that if you look at this timeline, that 1906, this Burgonian Tribondo study, we know that's reduced sensitivity. Then 1920s, reduced sensitivity correlated with the oxygen presence, that OER effect. Then how high energy photons interact with tissue, that Compton effect, and it has come. Then we have this importance of oxygen in radiotherapy, Nobel Prize for radiation-induced mutagenesis Drosophila, exponential quantification of the oxygen effect, all those studies. And if you see how radiobiology is now driving the radiotherapy treatment, it is the most important component. It is not just the physical dose, but it is a biologically effective dose for the success of the radiotherapy. And then you see all tumor potential, doubling time, ISO effect formula, differential radiosensitivity, early and late responding tissues, LQ model, and all which I will discuss. So all these studies to the timeline, it's a continuous study. So radiobiology is very, very important for success of the radiotherapy. Now I come down again. What is the primary aim of our radiotherapy? Our primary aim of radiotherapy is that deliver a lethal dose to the tumor, because we want that all the cancer cells are eliminated, all the cancer cells are killed, and that is a lethal effect we want. But at the same time, because tumor is not in isolation, tumor is surrounded by the normal tissue, organ at risk, critical organs, and therefore we have to spare the normal tissue, organ at risk, and deliver a lethal dose to the tumor so that we achieve a maximum tumor control probability. Now, how to achieve? It's a art, it's a science, it's an evidence-based medicine. It's an evidence-based, with evidence, and it's a tailor-made treatment. We have moved from the earlier era this. And now you can see radiobiology of the tumor and normal tissue, because if you see this radiation effect, this is a S graph, that's the graph, and this is the threshold. Below this, no radiation effect will occur. So sigmoid behavior, stochastic process is actually incidence of effect. And if you see it here, this is a tumor control and this is a normal tissue damage. This is there. Now, if I give this dose, I can expect maybe 10% of the normal tissue damage, but at the same time, I can expect about 60%. If I separate these curves by different fractionation schedules or different protocols, then I can deliver the dose much higher and I will get only 5 to 10% of the normal tissue damage, which is manageable, but at the same time, tumor control probability will approach to. Here you can see it here, that now with this dose, just 5% of the normal tissue complication, but at the same time, almost 90% of the tumor control probability I achieved. So it depends upon the volume. If it's a large volume of the tumor, the T4 lesion, T3 lesion, then the normal tissue and all complications will be also much more. But the smaller the field, smaller the volume, and now newer techniques like confirmation radiotherapy, IMRT, adaptive radiotherapy, IGRT, where tight margins are there, normal tissue involved is very, very less, so we can escalate the dose and with very less or manageable comorbidity, we can achieve a better tumor control probability. Earlier days radiotherapy, maximum dose we were able to give is 60 or 65 gray because of the complication into the normal tissue, because they were square field or rectangle field distributed, but now we have what a confirmed all those things. We can escalate the dose to 80 gray, 100 gray, 120 gray doses, and there we can have a very better tumor control probability. Now, 4 hours of radiotherapy are very, very important. Repair of sublethal damage. See, once lethal damage has taken place, there is no possibility of any repair. So, sublethal damage, which has taken place into the normal tissue, if you allow the graft, you give a fractionation, one fraction and gap of maybe 10 hours, 20 hours, then the repair can take place into the sublethal damage which has taken to normal tissue. So spares late responding normal tissue preferably. Redistribution of the cells in the cell cycle, because I told you cell cycle is going on and mitotic phase is the most sensitive. So one fraction and after a gap of some hours, if you another fraction, so acute damage will be into this will take place because of the redistribution of the cell cycle. Repopulation spares acute responding normal tissue, no effect on late effects, danger of tumor repopulation. And repopulation is very important, what is called as a kickoff time. Say after radiotherapy has started, after how many days? It is 3 weeks, 4 weeks, 5 weeks, slow growing tumor, fast growing tumor, repopulation will depend. And depending upon that thing, your total treatment time should be devised. If repopulation starts at very early, maybe after 2 weeks or 3 weeks, and your treatment is prolonging to 6 or 7 weeks, the cancer population repopulation, you will not be able to achieve the complete cure. Reoxygenation, because the tumor is there and on the surface the blood supply vessels are there. I will talk about the microvessels, blood, and how oxygenation will be there. They because of the presence of oxygen, the response cell killing will take place. And then after a gap, what happens is the cells which are anoxic today become oxic next day, because the dead debris cancer cells have been removed and then inside blood supply goes. So the possibility of reoxygenation. So repair of sublethal injury takes place, cell exposed, to spare ionization fields can be repaired. Killing requires greater total dose when given in several fractions, and that is what the fractionation. Most tissue repair in 3 hours to 24 hours, and that is the reason why our fractionation schedules conventional is 24 hours, hyperfractionation is 6 hours or 8 hours, allows repair of the injured normal tissue. So this is a repair. Deoxygenation, oxygen stabilizes free radicals. Hypoxic cells require more radiation to kill. Hypoxic tumor areas, temporary vessel constriction from mass, outgrow blood supply, capillary collapse, tumor shrinkage, decreases hypoxic areas, toxinate take place, reinforces fractionated dosing, hypoxic cell reduce sensitizer, selecting chemo. That is what I told about the sensitive. Redistribution, cell cycle, S phase radioresistance, but mitotic phase is the most sensitive. So rapid cycling cell more sensitive, and that is what you have to plan your fractionation. Repopulation, increase regeneration of the survival fraction. Rapidly proliferating tumors regenerate faster, and therefore you should go for hypo or extreme hypofractionation depending upon the alpha by beta. I will try to put forth what kind of fractionation schedule for which kind of tumor or alpha by beta is good. So these this is what 4 R's, and I can depict it here. Repair, as I told you, within 3 hours it starts. The redistribution, it may be just maybe 6 to 8 hours. Reoption is also immediately start, but repopulation takes a long time, depends upon the time of the tissues or this thing. So all this reoxygenation, redistribution, repair is in the period of some hours, but repopulation starts after days. So reoxygenation, redistribution, repair, repopulation, or regeneration, and they are all time dependent as a total treatment or treatment of the fractionation, how we have to do. Cannot achieve all at once, and therefore optimization of the schedule for individual circumstances, tailor-made treatment, fractionation of the radiotherapy is very, very important. And again, here I can show you how fractionation effect occurs. Here you can see 2 grade, 2 grade, 2 grade, 2 grade, this 1, 2, 3, 4, 5, 6 fractions of 2 grade, that's a 12 grade. And the effect I am getting this. But if I give the same 12 grade into this, the 4, 4 and 4, 12 gray, the effect will be much higher. So 2 gray into 6 fraction is not equivalent to the 4 gray into 3 fraction. Similarly, you can see it here, and therefore we arrive at the equivalent doses. So 4.8 gray 1 fraction is equivalent to 2 gray with 6 fraction. And similarly, the 6 gray into 1 fraction is 4 gray. So this is how, by this fractionation schedules, using the radiobiological model, we can move from one fractionation schedule to another, and we can find the equivalent doses required. So depending upon this thing, various fractionation schedules are practiced, and they are conventional fractionation, daily dose of 1.8 to 2 gray per week, 9 to 10 gray, total 40 to 70. Hyperfractionation, more fraction in a day, increase, T is kept the same, total treatment time, dose is less than 1.8, 2 or more than 2 fractions are given in a day. Spares late responding tissue is a biological basis. Accelerated fractionation, shorter overall treatment time. It is 1.8 to 2 gray dose per fraction, more than 10 gray per week is given. Hypofractionation, dose of 2.2 gray or more is given. Reduce total number of fractions, and rationally tumor has low alpha by beta ratio. I will just discuss what alpha by beta is and the therapeutic gain for prostate cancer, breast cancer, why we prepare the hypofractionation. And this is just a schematic conventional fractionation and hypofractionation. Total duration of the time is the same, but here number of fractions in hypofractionation are either 2 fractions per day or 3 fractions are given. accelerated fractionation, where the total treatment time is drastically reduced, but very severe early reactions will be there, and moderately accelerated, where almost treatment time remains the same, but the fractionation schedule is adjusted in a different way. Now, conventional fractions, the fraction size is 1.5 to 2.2 gray. Total dosage this spares early normal tissue reaction, allow reoxygenation, reassortment, and allow, this is what the advantage is. Hyperfractionation 1.15 to 1.8 gray, BID, that is a 2 or 3, 60 to 70, further separate early and late reaction. Accelerated fractionation, shorter time, reduces repopulation for tumor cells, no change in late effects. And hypo or extreme SRT, stereotactic radiotherapy or stereotactic body radiotherapy, where large fractions are given, reduced treatment time, convenient, better efficient with hypoxic cells. Now, hypofractionation also has been classified into moderate hypofractionation and extreme hypofractionation, where 6.5 to 10 gray per fraction for 4 to 7 fractions are given, or can be a single fraction SRS. And that depends upon the alpha by beta. Just within a moment, in next 2 slides, I will show what alpha by beta linear quadratic model. The tumor fractionation sensitivity low, alpha by beta ratio of a cancer higher than that of the late responding healthy tissues, more smaller size fraction. If alpha by beta ratio of the cancer is higher than that of the late responding, alpha by beta for late responding healthy tissues is of the order of 2 to 5. And head and neck cancer, alpha by beta of the tumor is almost 10 to 12. So alpha by beta of a cancer is much higher than the late, and therefore we need the smaller size fraction with higher total dose head and neck. But moderate to high alpha by beta ratio, for example, breast cancer, where alpha by beta is of the order of 5, almost you can say late responding normal tissue similar or slightly higher, there we can give hypofractionation, large doses, less number of fractions. And extreme hypofractionation, alpha by beta ratio of the cancer is much lower than the responding. For example, prostate cancer, where alpha by beta ratio is 1.5 or 1.8, much lower than the late responding tissue. There we go for an extreme hypofractionation, very large doses. Now, need to optimize fractionation schedule for individual circumstances tailor-made, and that is what we call time in which the doses are given, number of the dose, and the fractionation, and that all depends upon total dose what we are going to deliver, dose per fraction, time between the fraction, and the total treatment time. Now, radiobiological model have been proposed since 1945, and this is because all tumors are not treated with the same time dose fractionation schedule. Various schedules are used, various fraction schedules are used by the different centers. There are gaps, planned or unplanned. Then you have combination of the radiotherapy, brachy plus radiotherapy, external beam therapy, alter fractionation schedule, and we need, and this was the first, the Strandquist graph, what we call, for the cancer and the normal tissue, log dose and log time, and then the Cohen and Quimby analyzed. This is called the Strandquist, and that was the first relation based on this thing, the NSD, nominal standard dose, cumulative radiation effect, and TDF, time dose fractionation modules were given and being used. Still 1990s they were being used. But the recent one which we use for our clinical environment is a linear quadratic model, and it was proposed in 1982 and now being applied to radiotherapy. And the LQ model is a mathematical model. One is a linear and another is a quadratic term. Effect is equal to alpha d plus beta d square. We don't have to find out individual values of alpha and beta, where we can have only ratio. So where alpha and beta tissue specific constant for the head and neck cancer, squamous cell carcinoma, adenocarcinoma, the lung cancer, alpha beta, the prostate cancer, it will be different. Similarly, alpha beta for early reaction, late reactions will be different. Alpha beta for mucosal and normal tissue reactions will be different. And depending upon that thing, just I will not go into detail of the LQ model, but it is finally what we call ERD, extrapolated tolerance dose ETD, or extrapolated response dose ERD, or biologically effective dose BED, and it is given by n number of fraction, dose per fraction, D dose fraction, and alpha by beta of what effect you are going to take. It's for the tumor, if it is a late effect or early effect. And just one or two examples I will give it here how this radiobiological model is used. So acute epithelial tissue reactions in radiotherapy, normal tissue reaction alpha by beta is 8 to 13 with average of 10. Late tissue reactions I talked about, it can be 2 to 6. Tumor tends to be characterized by alpha by beta 10 to 25, but I told you prostate, it is 1.5 to 1.8. For breast, it is almost about 5. So for standard treatment of 2 gray fraction, 5 fraction per week, 60 gray dose, if you want to calculate the ERD, then there is an extrapolated response dose, then it will be 30 fractions of 2 gray, 2 divided by 10, where alpha by beta I have taken 10, it's a 72 is your ERD, and unit is gray. Now, ERD for late effects for the similar this thing if you want to discuss, and if you take the alpha by beta is 2.5, it will come to be 108. Similarly, ERD for normal tissue damage, if the alpha by beta is 8, it will be 75. Now, if you want to shift from 2 gray per fraction to 3 gray fraction, so how much total dose you will require? Will you require the same 60 gray? Just we'll see. So for standard treatment, ERD late effect is 108. My end point is late effect. And to get this much with a 3 gray per fraction, same late effect I'm going to get, how many fractions I will need to give. And therefore, n is equal to 106. So 16.36. So 16 fractions of 3 gray, that is a 48 gray, is a radiobiologically equivalent effect with the 30 fractions of 2 gray, that is a 60 gray. So how this is we can calculate, you can use. Similarly, 10 gray single fraction we are going to use, extreme hypofraction, will be equivalent to 28 gray by 2 gray fraction. You can just use this thing formula with the late effect as I end this thing, and you get 28 gray. Now, Dale has given for 2 fractions per day, 3 fractions per day, 4 fractions per day, the formulation, and this is the repair and the repopulation constant mu also have been included. I will not go into detail. For brachytherapy also, the ERD formulas are given, they are available in literature. Further, if the treatment is too long and the repopulation takes place, and therefore the time constant to take care repopulation during prolonged oral treatment time was added, because cell killing is taking place at the same time the cancer cells are growing. The effect will not be the same, it will decrease. And this is what the gamma or beta T repopulation constant it is given. And this is T is a total treatment time. TK is a kickoff time after which the repopulation starts. And I told you some tumors are slow growing, some tumors are very fast. The kickoff time is 3 weeks, 4 weeks, 5 weeks. Say, for example, breast cancer, it's a 5 to 7 weeks is a kickoff time. So now we have the terms, they are used into literature, they are all same. BED, biological effective dose, ETD, extrapolated tolerance dose, or ERD is extrapolated response dose. So in literature, we find this, and this is how same getting the same equi-ERD, equi-ETD, or equi-BED. applied to all types of the biological pattern, all types of the tissue, including the normal tissue. Now, tables can be prepared or tables are available. We have prepared this dose per fraction, alpha by beta. If you take 2, 3, 4, and total dose, equivalent dose from the table, like a TDF table we used to use, that can be taken care. So, for example, now I want alpha by beta 2 gray, so 200 centigrade, 6,000 dose. Now, if you just similarly what to create this thing. Now, for example, alpha by beta is 4 gray, the effect will be much higher. So this is how you can understand. So radiobiological basis of fractionation is that large dose per fraction, hypofractionation, increases the radiotherapy effect less in tissue with high alpha by beta ratio, large dose fraction more toxic to tumors with low alpha by beta ratio compared to tumors with high alpha by beta ratio. And therefore, tumors like prostate, breast, where alpha by beta ratio is less, extreme hypofractionation is more effective and it gives better result. Radiological basis of fractionation, small dose per fraction, hyperfractionation has reduced effect in tissue with low alpha by beta. So they are not good for tumors with low by alpha by beta ratio, that is a breast or the prostate, and therefore small dose per fraction protects the tumor with low alpha by beta ratio compared to tumors with high alpha by beta ratio. And therefore, in cases, tumors which has got low by alpha by beta ratio, the hypofractionation doesn't give a good result, but hypofractionation gives a good result. Hyper doesn't give. Now, just tumor biology. Again, you see there's a heterogenicity in a tumor in terms of the biological, number of chronological or stem cell. Very important thing in cancer treatment is that it is not the size of the tumor, it's a number of chronological cells into the tumor. Many times we find a T4 lesion completely regresses, we get complete response. But T2 region, there's a residual T2 lesion. This is because number of stem cells are more and we are not able to kill. Again, the proliferation will start. Therefore, increasing radiosensitivity, proliferative potential, pro-apoptic tendency, repair, that is a fast or slow repair, rate of repopulation, regeneration during therapy, doubling time, reoxygenation, redistribution, growth fraction, hypoxia, metabolism, post-cell infection, interstitial pressure, oncogenes, tumor suppression, these all heterogenicities affect the final tumor control probability. So it is not just the interaction of radiation with the tissue, but inherent biology of the tumor is very, very important for getting a good result. And also physical factor, there is a heterogeneity, dose heterogeneity or geographical miss, and this happens mostly IMRT and other things, a geographical miss, we miss the tumor part and residual end. So here you can see, now renewing of the stem cell, this is a stem cell, now it produces only one and non-stem cell two. This non-stem cell will produce only non-stems and this. So the percentage of the stem cell, how much is there? For example, here, 2 stem cells, again here, and if they produce non-stem cell, tumor. So how many stem cells they are multiplying, tumor regeneration, and success of radiotherapy is that you attack, you completely kill this tumor cell. And just one more, I will not go into details of this. Is tumor kinetics is another chapter where growth fractions will come, because it depends upon the cell cycle also. For example, cell cycle time is 36 hours and growth fraction, that is a number of stem cells, means out of 4 only 1 is stem cell, then doubling time is 6 days. So that is what a tumor log. Here you can see just if the chronological cell number is 10⁹ with 60 gray dose, almost about 60 to 70% tumor control probability will achieve. But if chronological cell number is 10⁻10 with 60 gray, I even cannot attain 10%. So larger the chronological cell number, larger the doses are required. But at the same time, normal tissue sparing and also the OAR, organoid sparing, is very, very important. If you can do that thing, you will achieve. Otherwise, you will end up into a residual stage. Hypoxia, another very, very important thing in success of the radiotherapy. And I will not go into detail because there's a blood vessel. And if you go away from the blood vessel, the hypoxia, the cells are deprived of the oxygen and they will be radio resistance. We do not get response, and this is a normal blood supply. And here you can see into the tumor, the blood supply gets occluded because of the occlusions, hypoxia gets created. And if you see the response, just 2 years response, small hypoxia fraction, you get almost about 80% of the tumor response, 24 months. But large hypoxic fraction is there, you get only 50%, so 40% tumor control. So oxygen plays a great role into the tumor control probability into biology. Again, 5 years or 7 years disease-free survival, oxygen supply is more than 10 mm of Hg. You can see almost about 75% of the tumor control probability at the end of 6 or 7 years. But if oxygen supply is less than 10 mg, it's almost 40%. Fraction plays. Similarly, the angiogenesis, the blood supply and blood, and this is what just example, more the micro vessels produced and the actually number of responses. There is a relationship between the microvascular density and the probability of metastasis, relapse-free survival, and the prognosis. So your angiogenesis also plays. Little bit radiobiology of the particle therapy I will talk, maybe 5 minutes, and I will end. This was actually the Robert Wilson. Way back in 1946, he suggested, why can't we use protons for clinical applications, because that time accelerators were available and all. And they started using based on the radiobiology. And you see it here as LET, that's a keV per micrometer, increases, the RBE increases and it approaches 3, 4, 5, 6, and then again overkill. So maximum optimal we can go if LET increases. So high LET radiation, we have high RBE, and that is what. And here you can see with proton, with helium, with these carbon particles, how much RBE you can get of the order of 4.54 you can get with this thing. And here you can see oxygen enhancement ratio, well oxygenated and hypoxic X-rays we are using, or photons. I told you oxygen enhancement ratio is of the order of almost 2.5. So here, if the cells are oxygenated, your dose required is much less, and you get a very good response. Survival of the tissue goes on. But hypoxic, much doses also you do not get. But neutrons, if you use, this gaps comes down, and alpha particles. So OER is almost 1. So the cells, the tumor is oxygenated or not oxygenated, alpha particle response will not differ. Again, LET and OER, you see it here, low LET radiation, and OER, if you see it here, high LET radiation, low LET radiation, OER is almost of the order of 3. As the LET increases, OER approaches oxygen dependence, and that is very important. And here you can see X or gamma radiation, you have OER and RBE. RBE is less, OER is more. And as you come down here, you have the protons, helium, carbon ions, and all. So almost you can see oxygen enhancement ratio approaches 1, but the RBE is more than 3. During this about 100 years of radiotherapy, we have from X-ray to cobalt to LINAC CDCRT to IMRT, and now you can see with this carbon particle with proton how much conformative index and all, because proton and carbon, they have a range, Bragg peak, they deposit, no exit dose, internal dose also will be less, so Bragg peak spread can be there, higher doses can be deposited. And here is a pictorial depiction of biological effectiveness and dose conformity. And you can see with this ions, carbon, neon, psi, the dose conformity is much higher. At the same time, the biological effectiveness is much, much higher. So with a less physical dosage, you get better biology. And this is how is a photon goes on depositing energy, the particles, Bragg peak, and you can spread this Bragg peak and you can deposit into tumor, and exit doses are very, very less with this thing, and that is what spares. Here you can see protons, photons, and IMRT, how conformation has taken place, much better than this, and the dose to 90% of the cochlea was reduced from 101% with standard photon to 30% the IMRT and 2% with the protons. And therefore, you can spare the normal tissue or OAR and give lethal doses. Carbon and are much better, expensive, but much better because of the sharper penumbra, more LET, more RBE. So with this thing, I end